Is differential equations. You have already done some work with differential equations. I just never bothered to call it differential equations. Jackie B in a nice, loud, proud voice. Can you read the big idea here? Where it says the big idea? Oh, on page 5. It's the one that looks just like this one.
In calculus, we are often given information about the derivative or the second derivative of a function, and are then asked to find the original function. Problems like these are called differential equations. Differential equations can be used to model real-life application problems involving signal analysis, population growth and decay, the flow of fluids, aerodynamics, particle motion. The list goes on and on. For those of you who plan to study engineering, science, mathematics, you will eventually study very sophisticated techniques for solving differential equations.
Okay, first of all, where are my future engineers? Engineering of any sort, structural engineering, civil engineering, mechanical engineering. You are going to take multiple courses in differential equations. Where are my future scientists? My future mathematicians? My future business people? The people working at McDonald's in the future. Okay. For one of those groups, probably differential equations not too important in your life. For everybody else, multiple courses in differential equations, and they are some of my favorite. Dr. Shama, who was about this tall and the toughest woman I've ever met in my life. She's the only woman I've ever known who was pregnant, gave birth, and returned to work the next day. She was from India, and she was like, we don't have maternity leave there. You just go back to work. She was amazing. Just such an inspiring professor. And someday you're going to have differential equations. Probably not with her. I think she retired. I'm old. She's older. But it was one of the most amazing courses I've ever taken. And unfortunately, we only get 9 days in the world of differential equations. So all my future engineers, I don't want you to roll into the course and be like, I know this, we studied in calculus. What we're going to study is going to get you through maybe the first 2 days of an 18-week course. And that's okay, but you're going to be just fine. Destiny, can you pick it up from there?
Yes. For our purposes, we will explore only a few basic techniques for solving differential equations. The first one for us to explore is anti-differentiation.
Anti-differentiation?
I can't say that. The integral.
Yep.
As we have seen, the integral yields multiple antiderivatives. This is why we use the positive c.
The plus c.
Oh.
Or Charlie?
Yeah, Charlie. If our final solution involves Charlie, we call these solutions general solutions. If, however, we are given enough information to determine the exact value of c, we can find the particular solution. This additional information generally referred to as the initial condition.
Excellent. So today is going to be like a skills day, and there's a couple of skills that I want to build with you, a couple of vocabulary terms that we're going to introduce, and you're all going to be just fine, because these are things that you already know. We're just going to use it in 3 ways. So let's look at this first one. We're going to solve our first ever differential equation. I'm so excited. Determine the function y equals f of t, which satisfies the initial condition, y of pi equals -2, and the differential equation dy dt equals secant squared of t over the cubed root of 8 plus 2 tangent t. New vocab terms here, differential equation. I would make sure that we got that. A differential equation just means an equation that involves derivatives. That involves derivatives. Okay. We've got an initial condition. The initial condition is just, it's your starting point. We've worked with initial conditions before. This dy dt is our differential equation, or as we say in the business, it's our diffie-q. Dy dt equals the secant squared of t over the cubed root of 8 plus 2 tangent t. I want to solve it. I want to find the original function. What function has that as its derivative? What are the instincts telling you to do? How are we going to find the original function if this is the derivative? You want to find the antiderivative, right? What we're after is the y. We want the initial function y. And as Jeanette said, we're going to find the antiderivative of secant squared of t divided by cubed root of 8 plus 2 tangent of t. And we're integrating with respect to t. Scary, I know, but I bet there are some folks with some smarticle particles who know exactly what you need to do. have a quick conversation with the friends around you. What are you going to do? How are you going to start? Already heard it from several groups. How are we going to start this problem? How on earth are you ever going to integrate something so ugly? So ugly. What are we going to do? Did you listen? Substitution. So if we're going to do substitution, we start with identifying the baby. And maybe the baby is obvious. What's the baby going to be?
8 plus 2 tangent.
8 plus 2 times the tangent of t. If that's the baby, then your next move, we're going to take the derivative. And let's get the variables right. I'm taking the derivative of u. The variable is t. I need du dt. So the derivative of 8 plus 2 tangent of t, well, derivative of 8 is 0. And now I need to know the derivative of 2 times tangent t. 2 times secant squared of t. Du dt is 2 secant squared of t. Depending on how you like to do your substitution, some of you are going to say, oh, I know what to do when you multiply both sides by half. Where are those folks? You'd rather do it that way? And then the other folks, they like to solve it for the dt. Where are those folks? I'm going to solve for dt because that really is like my favorite way to go about doing this. So I'm going to multiply both sides by dt. And so du is 2 secant squared of t dt. To solve for dt, we divide. And dt is du divided by secant squared of t. Rebecca, we're okay?
Yeah.
All right. So what's next?
For dt, plug in.
Plug in for the dt. I agree, but that's not all.
The u.
You also plug in for the u. So your new integral isn't secant squared of t over all this anymore. It's secant squared of t, and I'm dividing by the cubed root of u. dt is du divided by secant squared of t. And at first that looks bad because we're trying to do substitution, which means we want to get everything over to u. Michelle, any good news here?
No, you can cancel out the secant squared.
Oh, thank goodness. I can cancel out the secant squared of t and the secant squared of t. Anything else? Anything else that we're thinking about doing here?
Finding the antiderivative of
You definitely need to find the antiderivative. Sheila, what other thoughts you got?
Couldn't the du over 2 be 1/2 times d?
Okay, definitely that du over 2 is the same as 1/2 du, and this cubed root of u, I want to be careful, it's in the denominator. So that's really 1 over the cubed root of u. Daisy.
Can you also put like the u to the power of -1/3?
Oh my god, I love that. 1 over the cubed root of u, I'm going to rewrite as u to the -1/3. That half that I'm multiplying by, there's a big gap here, I'm going to pull that half out front. And we get to 1/2 u to the -1/3 du. Not done. Not integrated. Take a minute to finish this off. Some good stuff happening here. If I'm going to integrate u to the -1/3, we add 1 to the power, and you divide by the new power. So you're going to get 1/2 times 3/2 u to the 2/3. If all goes well, 3/4, 8 plus 2 tangent of t to the 2/3 plus c. How many guys honestly made it there? Okay, lots of folks in a really good place. Now here's the thing. The solution that I'm looking for, you might stop here. If you stop here and you still have the plus c, what we're going to do is we're going to call this a general solution. And the general solution can be just that. It's fine, unless they've given you more information. Did we get more information? We absolutely have gotten more information. Using that more information, we're going to figure out exactly what the value of c is, and we're going to move from what we call a general solution to a particular solution. So the initial condition says that y of pi is equal to -2. So I like to think of this and say, okay, so t is equal to pi, the y value is -2. All I need to do is plug everything in. Y is -2, 3/4, 8 plus tangent pi, 2/3 plus c. Yeah, it's ugly. For those of you that are not a big fan of tangent of pi, maybe you want to think about this as sine of pi divided by cosine of pi. So we've got -2 is equal to 3/4, 8 plus sine pi over cosine pi to the 2/3 plus c. What's sine of pi?
0.
What's sine of pi?
0.
Check it out in the unit circle.
Zero.
Pi, you're all the way over here on the left. The sine is always the y value. The cosine is always the x value. So 0 over -1, what's tangent of pi?
0.
Has to be 0. So -2 is equal to 3/4 of 8 to the 2/3 plus c. The only thing standing between me and c, I need to know what 8 to the 2/3 is. I take the cube root of 8, that's 2. 2 squared is 4. 3/4 of 4 is 3. If I don't blow it, c is -5. So your final answer is going to be y equals 3/4, 8 plus 2 tangent of t to the 2/3 minus 5. Now that we know what c is, that's a particular solution, not a general solution. How are we feeling? Jeanette, what's up?
Why do we need the particular solution?
So if you're given the initial condition, then I need you to use the initial condition so that you figure out what is the full function. Over here, if you say it's y equals 3/4, blah, 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 plus c, well, there's an infinite number of solutions. There's an infinite number of choices. As long as they have this form and you're ending in a constant, it works. But I have this other initial condition that you have to satisfy, and that's what's going to allow you to pin it down and say, oh, this is the one function in the whole universe that does this work. Gonzalo, you okay?
Yeah.
I just saw you were like, mm-mm. We got this? Michelle?
What happened to the two at the bottom?
What happened to the 2 at the bottom? This 2?
Yeah. No, like where it says 8 plus 2 10 of t, and then on the bottom. there's-
Oh, shame! Michelle, thank you for that. Thank you for making me a better teacher. Good news, it's still 0. And good news, I remembered the 2 at the end. Okay, for the most part, we're okay? This is a basic differential equation. This was a basic one. I know I went a little scary with it. Yes.
Oh my.
But it's okay. What I wanted to do is get a good review in there of integration by substitution. Adrian, you doing okay? You look like you're having deep thoughts on a Monday morning. Congratulations, skill 1. Check it off the list. High five your neighbor. You've got this under control. All right, skill number 2 coming your way. Sometimes you are not going to be asked to solve a differential equation. Instead, they're going to give you the differential equation, and they're going to say, hey, friend, go and prove that this thing is a solution. Let me say that again. I need to make a mental note here. Don't use the green marker. It makes you sweat. Okay. So let me back up on that and face you all as I get a little glistening here. Way back in Algebra 2, you might have been asked to solve an equation like x squared minus 5x plus 6 is equal to 0. What would you do back in Algebra 2?
Solve for x.
You would solve for x because that's what the instructions tell you to do. And there was a technique that you had, right? You would do the x box. Somebody said they would factor. You would do all manner of things. And ultimately, you're going to get to x minus 2 times x minus 3 equals 0. And you know that x is equal to 2, or x equals 3. Easy peasy Algebra 2. Did anybody ever get one of these questions on a multiple choice part of the test and you had no idea how to solve it?
Probably.
Probably. Ever get to one of those problems and they're like, which one of these is the answer choice? X equals 2, x equals negative 2, x equals 5, and x equals negative 1. Anybody ever in that situation?
Yeah.
Jose, what did you do in that situation? Be honest. What did you do, Jose?
I guess.
You just blindly guessed?
Not blindly, but I plugged in.
We would plug in. You would say, gosh, I don't remember how to factor. I got hit in the head by a rock on the way to school today. And so what I'm going to do is I heard you say, and a lot of people said, right, we're just going to plug in. Henry, you said you would plug in. How do you know that you found the right answer when you do this plug-in step?
It equals 0, because the equation equals 0.
Okay, so you start with the first one and you say 2 squared minus 5 times 2 plus 6, does that equal 0, right? And you go through and you do the math to figure out if it works. We're good? Same idea in differential equations. Same idea. We want to show that for any constant c, the function y equals c times the square root of x squared plus 4 will be a solution to that differential equation. The y equals c times x squared plus 4 is your solution. This guy over here is your differential equation. And they're not asking you to solve it, because quite honestly, we don't have those skills yet, but they're coming. All I want to do is show that it actually is a solution. And just like we would have done back in Algebra 2, when you didn't know what to do, we're just going to plug in. Everybody okay?
Yeah.
We're just going to plug in. But what you're plugging in, how you're plugging it in, you want to be really careful. You've got to look at the differential equation, and the differential equation says take x squared plus 4 and multiply by what?
dy
over dx, which is the derivative. So they gave you the original solution, but to do the plug-in, you need to find the derivative. Go give me the derivative. We know y is equal to c times the square root of x squared plus 4. So dy dx, be careful, c is a constant, times the square root of stuff. That's going to be 1 over 2 times the square root of the stuff, times the derivative of the inside is 2x. And everybody's okay with the derivative? Okay. So the left-hand side says take x squared plus 4 and multiply by this derivative. Okay. And what it's supposed to equal is x times y. It's like when you were back in trig class last year, and you were doing all those trig proofs, and you had to work one side to get it to look like the other side. Is there anything that we could do here that maybe would make life a little bit better, a little bit prettier? This is the left-hand side. Your goal is to get to x times y. See, Karina's got some ideas. Is there anything you could do here which maybe moves you forward? Karina, get us started.
We could take the square root, the bottom off.
What do you mean take that?
Like, multiply again, square root of 2 plus 4, like, you know, like a fancy one.
Oh, so you want to multiply by 2 square roots of x squared plus 4 and 2 square roots of x squared plus 4. Is that legal?
No.
Right, it's fancy one. I don't know that that's what anybody was actually thinking about doing, but okay, let's see what happens. We've added this into the mix. Looks a little ugly. Oh my God. That's the fattest, ugliest, fancy one I've ever seen. Well, what happens? 2 square roots of x squared plus 4 times 2 square roots of x squared plus 4 is really 4 times x squared plus 4 on the bottom. I've taken care of multiplying those together. In the numerator, I've got x squared plus 4 times c times 2x times 2 square root of x squared plus 4. This may not have been what anybody else wanted to do. Your goal is to get to x times y. Is there anything else you can do to get there? Do you know what he's saying?
Can you cross out the x squared plus 4 in the numerator and the denominator?
Is that okay? Right, it's all multiplication in the numerator, all multiplication in the denominator. Anything else? Anything else you could do? Destiny, what else could you do?
If you want
The x squared plus 4 and the x squared plus 4 cancel out. That's good. That's good. Sheila, what do you say?
Can you simplify the 2x and the 4?
The 2x and the 4, how would you simplify?
Like divide each by 2, so
Okay.
it'll be like 1x over 2.
Okay, so now you've got 1x over 2, and if you're going to do that, there's something else you can do? Paul, what you got?
The 2.
The 2's are going to cancel each other out. What are you left with now is c times x times the square root of x squared plus 4. Is that what we're trying to get to? What you're trying to get to is this expression on the right-hand side where it just says x times y. Did we get there? Oh, are we sure? I see c times x times square root of x squared plus 4.
Oh yeah.
Right, Henry, you see it now?
Yeah.
What do you see?
That says y equals that equation.
Yeah?
You just plug in y into the differential equation.
Right, this guy over here is what y is equal to. So you're fine at the end, you've got x times y, which is your right-hand side, which is what you were after. Karina, nice job. This is not what I was thinking, but that absolutely works. Marilyn.
I was gonna ask if you didn't do that,
What I was hoping somebody was going to recognize is that you've got x squared plus 4 to the first power, and down here you've got x squared plus 4 to the half power, and you could subtract the exponents, and that would get the square root of x squared plus 4 in the numerator a little bit faster. Either way works. Okay. This is what you would do if you didn't solve it directly, but they said, hey, show that this is a solution. Okay, with that said, I want you to try 3a. Same kind of idea. Show that for any constant c1 and c2, this guy here is a solution to that differential equation. I'll walk around and check in with some folks. Yeah. So we're taking notes, you're taking notes.
Every day, yes.
It's stolen. There's that value already. Here's your solution. This guy here is your differential equation. So a lot of folks off to a good start here. You need to show me that that is the solution to the differential equation.
Does it matter that b is squared?
Yeah, what does that mean? X squared y dx squared? This is the second derivative. So what we're saying here is that the second derivative plus 4 times the original function has to be equal to 0. That's what you need to show. Okay? So I've seen a lot of folks that said, okay, well I know the original function is c1 sine 2x plus c2 cosine of 2x. How do I get to the second derivative? You find the first derivative first. First derivative, c1, which is a constant, times sine of 2x. So it should be c1 times cosine of 2x times 2. c2 times derivative of cosine is negative sine of 2x times 2. And I think most folks had that. We're good with the derivative part? Okay, now I've got to go and I've got to take another derivative. It might be worth cleaning this up a little bit first. So c1 times cosine of 2x times 2, I'm going to write as 2c1 cosine of 2x. c2 times negative sine of 2x times 2 is negative 2. Negative 2c2 sine of 2x. That's the first derivative. Go get me the second derivative. d squared y dx squared. That's what I want to see. Derivative of 2c1 times cosine of 2x. c1's a constant. 2c1 is a constant. These are constants I'm multiplying by, so this should be 2 times c1 times the derivative, which is negative sine of 2x, times 2, minus 2c2, still a constant, times cosine of 2x, times 2. Clean it up if you want to. 2c1 times negative times 2 is negative 4c1 sine 2x minus 4c2 cosine of 2x. Is everybody okay with the derivative?
Mm-hmm.
Or I guess derivatives that we're doing? Okay. You're not done though. Of course you're not done. What is it that you're trying to do? You've got to prove that this function is a solution to this differential equation. And so Henry's advice from earlier, when you were back in Algebra 2 and you didn't actually know how to solve, but you needed to like figure out what the answer was anyway, is just plug in. Well, the formula here says on the left-hand side, take the second derivative and add it to 4 times the original function. So your second derivative is negative 4c1 sine 2x minus 4c2 cosine of 2x plus 4 times y. Well, your original is c1 sine 2x plus c2 cosine of 2x. Does that actually work?
Yay.
Yeah. Destiny, you're convinced that it works?
Yes.
What are you seeing happening?
So I crossed out the minus 4c1 sine 2x with the plus 4c1 sine x.
Where do you see plus 4c1 sine 2x?
Oh, I put it where it says in the equation for y.
Yeah?
Is y is c2 cos of 2x, I mean sine of 2x.
c1 sine of 2x. And
So
then
I
this,
crossed that out with the negative 4c1 sine of 2x.
wait, you crossed out this one and that one?
I crossed out the negative 4c1 sine x with the 4c1 sine x.
Okay, it just there's one thing I haven't heard you say, and I know it's in your head and you just know it, right? Daisy, what's the thing that she hasn't said yet?
Distribute the 4
You-
into the original function.
Right, Destiny, I knew you absolutely did that, right? But that's negative 4c1 sine 2x cancels out down here
Yeah.
after you do the distributing, and those cancel. And good news, the negative 4c2 cosine of 2x and the 4c2 cosine of 2x, those guys cancel as well. And what are you left with?
0.
You're left with 0, which is your right-hand side, which is what you're after. Usually these problems where you're given the solution and you just need to prove that it works, it's just going to be a matter of plug in, follow the recipe, make sure that what you get on the left-hand side, it matches what's on the right-hand side. Henry.
I don't even know what just happened. Like,
A lot of beautiful calculus happened.
because I just see the 4 outside and like everything got crossed off, so I don't know why.
Okay, so this negative 4c1 sine 2x and the negative 4c2 cosine 2x, this was the second derivative that we found. But the differential equation says take the second derivative plus 4 times the original. There's your second derivative. This is 4 times the original function. And what Destiny said was multiply through by the 4. So now you'll have 4c1 sine of 2x, but you already had a negative 4c1 sine 2x. As ugly as those are, they're opposites of each other. And when you add them together, you get 0. Same thing's happening over here. Thanks, Daisy.
No problem.
All right. Love starting differential equations on a Monday. We're deliberately going to skip part B because I want to end with the word problem. Oh, no, it's wonderful. This is how you grow as a mathematician. Of course you do, Daisy. Everybody wants to be one. Mauricio Ruiz just told me that he's become a mathematician. And now he's emailing me to like do his homework for him.
I don't know what I did.
Mal?
About slope fields, which is differential equations. Except he got confused and said I need help with force fields. It was very confusing. All right, Paul, can you read the word problem?
Ice is forming on a pond at a rate given by dy over dt equals k squared t. Where y is the thickness of the ice in inches at time t measured in hours since the ice started forming, and k is a positive constant. At t equals 9 hours, there are 4 inches of ice on the lake. Find y is equal to t.
Okay. This is the last skill we're going to try to develop today with differential equations. Differential equations are going to show up as word problems. There's lots of applications. So, first of all, does this actually count as a differential equation problem?
Yeah.
Is there a derivative equation somewhere?
Yeah.
Yeah.
Absolutely. We've got this dy dt. dy to, sure, why not? dy dt equals k times the square root of t. That's your differential equation. I want to solve this differential equation. I want to find the original function. What are we going to do?
Antiderivative.
Right, we're going to go and you're going to find the antiderivative. Finding the antiderivative should be very much within everybody's skill set here. So take a minute, go find me that antiderivative. Antiderivative of k times the square root of t. You're integrating with respect to t because t is the variable. K is a constant. T is the variable. careful. Some of you are finding derivatives, and what I need you to find is that antiderivative. In the antiderivative, exponents get bigger. If it's helpful, maybe rewrite square root of t as t to the half. Okay, Diego, what's the antiderivative going to be here?
K times 2/3 of t
K times 2/3 t to the what power?
to the 3/2.
T to the 3/2. I like it, I don't love it. You are so close. Plus Charlie. Now I'm curious, did any of you guys just see that constant and you factored it out in front of the integral? Nobody did that? But everybody's okay that that could happen? Okay, good. So now we know that y is equal to k times 2/3 t to the 3/2 plus c. Here's the problem though. What kind of solution do we have? There's two flavors. There's general solution and there's a particular solution. And this is a general solution. I need us to get to the particular solution, which must mean that there's an initial condition somewhere. There's actually two initial conditions. There's two. Jalissa, do you see one of them?
K is a positive constant.
K is a positive constant. I agree with you. That's not necessarily an initial condition, though. Paul, what do you say?
At t equals 9 hours, therefore, inches of ice on the lake.
At t equals 9 hours, there are 4 inches of ice on the lake. Okay, so t's equal to 9, y is equal to 4. That is one initial condition. There's another one, and it's hidden from you. An initial condition tells you a connection between the time and the y value. Destiny, do you think you see it?
I was going to say K is a positive constant.
K is a positive constant, but when we talk about initial conditions, we're looking for like, at this particular time, the y value is equal to this particular thing. It's really subtle, and the fact that no one's really seeing it yet isn't a surprise. You've got to think about the situation. Is there a time that you know the y value? Henry, do you see it?
At 0,
Times 0, what do you know?
that the ice is like, there's no ice.
At time 0, how much ice is there?
None.
There's absolutely no ice. That is one of the, it's like a hidden initial condition. It's not obvious. This guy over here is more obvious. This one you got to dig a little bit. Paul.
Do you need both in this one?
Well, let's see. If all you had was the one, if all you had was the first one, then what happens? You're going to say that 4, oh that's a bummer. 4 is equal to k times 2/3 times 9 to the 3/2 power plus c. Right, if that's all you have? Now 9 to the 3/2, you guys know what that is. Oh gosh.
27.
Right, square root of 9 is 3,
Yeah, 3.
and then 3 cubed is 27. So 4 equals k times 2/3 times 27 plus c. You're going to get 4 equals 18k plus c. You get stuck here if that's all you know. Jeanette?
Where does it say that t is going to equal 0 and y is going to equal 0?
You need to understand the problem. It says ice is forming on a pond at a rate given by this, where y is the thickness of the ice in inches at the time since it started forming. So at time 0, there is no ice. That's when you start forming the ice. That one's tricky. Is everybody okay with getting here?
Yeah.
But the problem is you're stuck.
Yeah.
Right, and because you have 2 variables in one equation, you can't do anything. So you use the other condition. What happens if you use the other condition? You get 0 equals k times 2/3, 0 to the 3/2 plus c. Good news. 0 to the 3/2. 0 times 2/3 times k. 0. So 0 is equal to c. Okay. Daisy is faking her way. Oh wow! I didn't see that coming.
Okay, that wasn't me. That mine was like very low.
Okay. We're good with c is equal to 0. So what's k? K is 4/18. If you want to show off your skills, you can reduce to 2/9. Your final answer is going to be that y is 2/9 times 2/3 t to the 3/2 power. Or even better, y is 4/27 t to the 3/2. Okay. Before we take any questions about it. Everybody was okay with solving the initial differential equation? Right, just the integration piece? I think most of you are okay with the obvious initial condition. And the hidden one, they're usually not going to be hidden like this. Okay. There is one thing that I'm going to do to make this work. So Eval and then Karina.
How do you know what initial number to plug in? Like, how do you know to plug in 0 for C and then plug in 9 and 4?
So that just has to do with the wording on this question, right? It says, y is the thickness of the ice in inches at time t measured in hours since the ice started forming. So we're assuming from that statement, if the ice started forming at time 0, how much ice is there? Right, the ice starts forming now. There is no ice at the very beginning. You're going to have to read deeply on that one. All right, I just want to close out with the vocab moment. We've got about 3 minutes. I just realized I never put the homework on the board. Yes, there is homework. Yes, indeed, there is homework.
It's too late now, mister.
No, it's never too late.
You missed your
2
shot.
nights
No
homework.
homework.
Shut up, Daisy. I was just starting to like you again. All right, 2 nights homework is assignment 107, questions 1 through 6. Don't pack it up.
Are they easy questions?
Oh, yeah.
Easy for you or easy for us?
Oh, it was easy for me.
Okay.
1 through 6.
107, 1 through 6. All right, we get 2 minutes left. We're just going to get started on this, and it's going to be all right. I need to close out with the vocabulary moment here. All of my scientists, you've probably seen this before. We say that the quantities x and y vary directly. I want to make sure we box that. Or are called proportional. 2 things are proportional, meaning that they satisfy this relationship that the first one is a constant times the second one. K is some positive constant. If 2 quantities are inversely proportional, it means that the first one is a constant divided by the second one. Directly proportional, y equals k times x. Inversely proportional, y equals k divided by x. Here's an example. This is fiction. My wife and I have decided that for every one of you that signs up for the AP exam, takes the AP exam, Rebecca, and gets a 5 on the AP exam, you're going to get $100.
This is better start studying.
If you look at the number of people that take the exam and the amount that we pay out, what kind of proportionality relationship is that?
Direct.
It's direct, because if I double the number of people that get a 5, what happens to the amount of money? You double. That's a direct variation. But what if instead we say, you know what, that's too expensive because there's 45 kids, they're all going to get 5. Instead, what we say is there's $1,000 available to be shared by every single person that gets a 5. 2 people get a 5. How much money? 500. Double that. 4 people get a 5. What happens to the amount of money? Not just decrease. You double the amount of money, you cut in half. I'm sorry, you double the number of 5s, you cut in half the number. So an inversely proportional relationship y plus k divided by x. More on that tomorrow. I'll see you guys later.